Hello, good morning to everybody. Thanks for joining in. And good afternoon to everybody who's on a different time zone. It's great to be here. My name is Gilles Perez. I'm the product marketing lead here at Groundcover, and I'm joined today by two of our founding engineers, Noam Levy, who should be on your left-hand side. Hello, Noam. And we have also Aviv Zohari, who is on the right-hand side. So thanks everybody who's joining in. We're going to let a few people join in to this exciting webinar we have coming up about Kubernetes. So for those who don't know, Groundcover is an observability platform and the only one who is both Kubernetes-native and powered by our own proprietary eBPF sensor. And today we're going to focus on Kubernetes, such an exciting platform. For those, I'm sure it's familiar for everybody. It's Kubernetes is a container orchestration system. And let me just, before we jump into some cool insights from Noam and Aviv, just want to share with you some stats. I love stats. So Kubernetes was created in September 2014. Kubernetes 1.0 was actually announced in July 2015. Some of the early contributors to Kubernetes, to the Kubernetes project, were Docker, Google, Microsoft, IBM, and Red Hat. The Kubernetes project has had a very strong community support and a vast ecosystem with over 2.8 million contributions made to the Kubernetes codebase, made by over 120,000 developers. So really huge community. And in 2019, 4 years after its release, a CNCF survey reported that 78% of companies were either using Kubernetes or evaluating it. And in 2022, that number actually skyrocketed up to 96%. So huge adoption, huge interest in this system. Today, it's believed that over 6 million developers are using Kubernetes. So should be familiar to most of you, if not all of you. And I'm sure most of you are actually using Kubernetes. But diving into our first question for today, Noam, can you explain such a huge surge in interest and adoption in Kubernetes?
So I think that in general, Kubernetes was from the way I see it, Kubernetes was like the big champion of enabling companies to shift towards microservice-oriented architecture. So we all started building application as those huge monoliths that usually runs on single servers, and microservice-oriented architecture was very appealing to confront the challenges of higher traffic rates, spiky rates of traffic, but there was lack of good tooling to accompany all the challenges that microservices-oriented architecture brings along with. And I think Kubernetes was the first truly production-ready way to have a declarative procedure of automating the orchestration of fleets of application that are constructing together one business logic as a whole. So I think this is like the big revolution that Kubernetes brought with it. It made it possible for even the tiniest startup to the largest enterprise to start breaking down their applications to multiple services and to make it possible to manage and to make it even efficient. It has its own challenges, of course, but I think that the fact that in 2023 we are able to build applications that are ready for millions of requests a day, even an hour, from day one, is an amazing achievement that a lot of it can be contributed in a lot of ways to Kubernetes being so accessible.
Yeah, so I think I'll follow up on that. The flexibility part of Kubernetes is really amazing. It's outstanding. So you can be a small startup having one small production cluster, and you can be a huge corporate with thousands of clusters. It doesn't matter. Kubernetes will be able to do what you need and handle all the load, the scaling, and do all the things that you need to make sure that your environment keeps going. And it can work on cloud environments, of course, cloud native. All the big names have their own versions of it, but also it can be on an on-prem installation. You can actually manage Kubernetes on your own, and it fits. It's one thing that fits for pretty much everything. Also, it has all the primitives that you need to build all types of applications. So you can do short-lived jobs on it, like very quick jobs, and you can do long-lived databases. Basically, you can build everything, and Kubernetes has your back in doing that.
So, Noam, you mentioned in your answer, you already mentioned that it does have its own challenges, and as with many or most good stuff, it comes at a certain price. And with Kubernetes, it does create its own set of monitoring and observability challenges that are unique to Kubernetes environments. Maybe Aviv, can you continue talking about what these challenges are?
Yeah, so I think that the way I like to think about it is that Kubernetes is magical in many ways. It gives you the sense that everything just works out of the box. But in reality, the magician has to work hard here. So there's a lot going on behind the scenes. And this means that sometimes you might be affected by Kubernetes itself in ways that are hard to understand if you don't have the right tools to look at what's going on. So just as an example, Kubernetes has its pretty complex system of how it manages your deployments. So there's the control plane, which is like the mastermind behind the scenes. It has kubelets, which are deployed on every node, and there's a lot of things that have to work together in order to make everything happy. And sometimes that might not work as expected, and you might see things such as pods not being scheduled, and you have no idea why. Or you see that some APIs are taking longer, like APIs with Kubernetes are taking longer than they should. And if you don't include the right tools in your stack to make sure that you know what's going on with your Kubernetes environment, then you're probably going to end up surprised at some point about something that you haven't foreseen and don't know how to troubleshoot.
Yeah, I think that I'd like to add on that I think that because Kubernetes allows to add to build such complex apps in A's relative to the past also means that things are getting complicated very quickly. So, and when things get complicated very quickly, you need to have like a good strategy for day one to how you troubleshoot and tackle problems. It's not like that we have the we can't it can't be like an afterthought how we address problems in production, in development, etc. Kubernetes requires us to think our monitoring and troubleshooting strategy basically from day one, because our fleet looks very and operates in a very complicated or complex way from day one.
Great. So thank you both for those insights. I think we want to go. We talked about some of the challenges and some of the advantages, but I think we also talked about how groundcover is a unique observability platform in the sense that it is both Kubernetes-native and powered by our proprietary eBPF sensor. I want to try to show the audience a few actual use cases of what troubleshooting Kubernetes issues might look like on our platform. And so I want to dive into basically the main event, the main part of what I think most people are here to see, which is how do you actually troubleshoot those issues. So Aviv, I'm going to start with you, and we can start by showing one use case, and then we'll move over to showing Noam's use case as well. I do want to urge the audience to send us your Q&As. If there's any questions along throughout the webinar, you can definitely send us your question using the Q&A section. So feel free to do that as we go along. And now I'm going to pass it over to you, Aviv.
So at this specific use case, we're given the task as a developer of figuring out why some service is occasionally breaking. So basically, you can imagine that some users of some application are complaining that every now and then the application breaks. Imagine this is some sort of the UI, some sort of web server that occasionally returns bad responses, and we're trying to understand why. So I think that the first thing that a lot of developers would do in this case is go ahead and check the logs from the service they think is the issue. And in this case, we're going to be starting with this service called frontend, which is the first point of contact that a user would be encountering in this specific service. So if we look at the logs here, then we can see a lot of things are going on. Requests seem to be handled, but up here in the graph, we can see that it looks like there are some errors. So if we go ahead and filter by the errors, then we can see, just open this one of them, we can see that there seems to be an error with something handling something and connection being refused. So that's not very indicative. But also we can already see that this looks like a real issue. And actually, if we go ahead and check out the traces that happened at the same time, then at the same time as this log line, then we can see that the server did indeed return this 500 internal server error. So this is a good point to start by understanding that this will definitely mean the server breaking for our users. So this looks like we found the issue, but is this actually the real issue? Is this the core issue? So the way to progress from here, I think, is by going into what we call the service page, which is basically all the information that you want to be seeing when troubleshooting a specific service or workload. So looking at this page, we can see the availability of this deployment. And you'll notice that this speaks Kubernetes, right? We have the pods here. We have on the right the metadata about what is this deployment, what's going on here. And we can also go ahead and check out the resources that this deployment is using, how much CPU and memory, check out the node that it's running on. And nothing here looks really suspicious or bad. So let's see what happens if we check out the APIs. So this is basically all of the APIs for that specific workload. And here we can actually see this pattern of errors that are being returned from this server. And it's pretty cool because we mentioned that we are looking for something that happens occasionally, but not all the time. So it seems like we have, at the very least, found the behavior that we're looking for. But how do we continue from here? So if you remember, the log line had this description of being unable to connect to somewhere, like connection refused error. So it's very likely that this has to do with another service. And this is classical microservices architecture, right? The front end is just the front end. It's not the entire system. It's not a monolith. So we have to have this context of what other services exist and who front end communicates with. And we can do that in bottom here, and they have the service map. And we can see the front end is serving requests from this client, which is, by the way, you can see this red node. That means that there are errors here. But it's actually communicating with this other service that's called a struct server. And here, if we take a look at the traces, for example, all the traces that are recorded, we don't see anything bad. So we don't see anything that screams, well, there's an error here. And if we go and take a look at the logs of this struct server, which I won't do just for saving time, but I can promise you that there's nothing bad that seems to be happening there either on an applicative manner. So what do we do from here? Well, the obvious thing to do, like we just did here, is go ahead and check out the page for this specific workload, this other service, this struct server. And if we go ahead and do that, then right away we see something that we didn't see before in the previous one, is that the availability section looks not good. So basically, the service is crashing. We can see those dots here every time it crashes. We can see it restarted 115 times. And in general, obviously something bad is happening. So, okay, but how do we know what exactly is happening. So if we go ahead and, for example, start with the APIs it's serving, then everything looks okay. I mean, there are no errors. It didn't return some other 500 error or anything else. And it looks like, well, an application level, everything looks okay. But this is why we also have the resources tab, for example, because we see that the pod is crashing. But why is it crashing? So one of the key reasons I think almost everyone who has ever deployed something to Kubernetes is familiar with is not giving enough resources to your pod. And we can actually take a look here on the right and see that the pod is kind of close to reaching the limit. Like over here at the very right, we can see this peak of memory that seems like it's almost touching this dotted line, the red line, which is the limit. And in Kubernetes, if that happens, then your pod is going to be restarted immediately. And actually, if we can also do this exercise, if we count the number of peaks here, so there's about 6 of them, and we go back to the infrastructure tab, and we can see there are actually 6 crashes. And these align with the memory usage. And this basically gives us the ability to learn that the pod probably needs more memory. Now, why does it need more memory is a question for another day. But at the very least, we know that front-end experiencing those weird hiccups where it suddenly is not able to serve the clients is actually a result of another pod that is crashing because it doesn't have enough memory. And we'll talk about this a bit more at the end, but just as something to think about, this would be very, very difficult to understand if we didn't have this context in one place, being able to look at different workloads that are communicating with each other and pinpointing the things that are not application itself, but rather Kubernetes behaving in ways that affect your application, such as killing it if it exceeds the memory limits. Yeah. So we can move on to the next example, Dil.
Perfect. Thank you very much, Aviv. And just before we do that, I'm gonna give you guys a minute for Aviv to mute himself and Noam to put himself on speaking mode. Thanks for that. I think the next use case we're going to go into is also going to show you some new features, that were part of a recent release, where we're going to show you how we use the noisy neighbors, which is a very cool feature. I will remind everybody, if you have any questions about what you see, I know a lot of you online right now are actually users of the platform. So, if you have any questions about, the new features or whatever you see here for the first time, or maybe a different way to use what you're used to seeing, then feel free to ask in the Q&A, or if you can't find the Q&A, you can just put it in the chat. That's totally fine. And now we're going to hand it over to Noam. One small second, yeah.
So the thing I'm going to demo now is basically kind of a mirror image to the problem that is very popular in Kubernetes that Aviv just showed, and basically how pods are limited, how pod limitation can affect the application performance. Following up on that point, I think that in general, it's very important, and a very important notion to understand about Kubernetes is that, first of all, our applications are sharing the same resources with applications that can be completely uncorrelated to our application. We can have a huge traffic we can have an application that serves thousands of requests per second, while an application on the same exact node can be dead silent. And on the contrary, we can have two applications that are experiencing a huge spike in traffic, and we are not necessarily and they are not necessarily serving a lot of traffic at the same time due to the same reason. The most basic example for it is, let's say, a company that have a single Kubernetes cluster for two complete different divisions in the same company, and those things can sometimes affect each other. So the spike in one application, in one workload, can affect the performance of another. This leads to the same conclusion that Aviv mentioned earlier, that basically in Kubernetes, we can't really navigate through problems without having the full context. So level 1 context is fetching all the logs, metrics, and traces to the same place like Aviv showed you. But context stretches far more than just the pillars of observability. It stretches to what other applications are doing while my application is serving traffic, because this can affect my application no less than the boundaries that are set on my application by me, like for example pod limitations. This problem is also more apparent when we are talking about the fact that sometimes me as a developer is really I'm being really I'm not aware of where my application is going to run. I'm not aware of how many resources it is going to being able to use at peak hours, and I can find myself and my application can easily find itself in a node alongside a workload that is serving millions of requests per hour, thus preventing me from utilizing resources to serve my own application traffic. And this is the demo that I'm going to show now. So I have this application in my production namespace called my API deployment. As you can see that the application served around 4,000 requests per minute. And then all of a sudden, huge drop in throughput. Users are probably experiencing slowness at that time period. I haven't changed my deployment. Let's say this is Black Friday and there was a tag freeze. Nobody changed version whatsoever in the production cluster. But then this sudden drop in throughput automatically fixes itself. Now this is the most disturbing kind of problem. The problems that are appearing for, let's say, 30 minutes and then all of a sudden recovers. My company probably lost a considerable amount of money here due to bad user experience. And I need to understand what happened and how to prevent it from happening again. Now the only thing I am aware of in most circumstances is my own application, and I already eliminated the possibilities that this is due to a version change or to some bug in my program. And I want to understand, and I need to have more context in order to get the root cause. As you can see, not only that the throughput was down in a considerable amount in this time period, but also the latency spiked. So every request I've served during this time period was also taking longer to be served and to be fulfilled, making it even prone to more timeouts eventually. So in groundcover, in order to help you tackle this problem in a single screen and and eliminate the need to speak with different division, with the SREs, or maybe with the person that was on call during the moment of the outage, we created the resources tab in the workload overview and added a new box called noisy neighbors. So if I will just take, let's say, the last 6 hours, I need to cool. So as you can see, my pod utilization during traffic hours was considerable, and then all of a sudden the CPU was throttled down, although the traffic haven't changed. If I will go to the noisy neighbor tab, I can see immediately that during that CPU drop, there was this new workload on the node. In here, I called it high CPU, CPU stressor deployment, that all of a sudden took basically all of the cores that were available on the node. This caused my service to being throttled from CPU, thus resulting in the API request serving throughput drop that I saw earlier. Now, this is something that is very common in Kubernetes due to a varying reasons. It can be a workload that is also experiencing a traffic spike and was not guarded correctly for CPU, or maybe has some bug that when the traffic grows linearly, the CPU grows exponentially for some reason. It can be a manual backup job that was scheduled in Kubernetes during the night. Think an example that I saw among at least 10 customers is a daily backup jobs that copy the entire DB to an S3 bucket or all the logs to an S3 bucket, utilizing basically 90% of the CPU or memory. And during that backup, basically all the workloads are being throttled and the throughput is going down considerably. This insight allows you to build a better orchestrating strategy in Kubernetes. For example, one of the possibilities to do in such circumstances is to add tames to the node and prevent and by using node selectors and tolerations, I can decide to schedule highly CPU intensive applications to only specific nodes. So I can guard specific applications from throughput if they are important for me to have a consistent throughput throughout the day, regardless of my cluster utilization. I can also use the node affinity feature in Kubernetes, or anti-affinity to help Kubernetes take scheduling decision that, for example, always keep specific namespaces that will keep namespaces apart in node scheduling when it decides where to schedule each application from different namespaces. This is a classic example in organizations that share a cluster, and a namespace is there is a namespace per division, and you would like to make sure that those different divisions are not sharing specific nodes to prevent the workloads to affect each other. And of course, needless to say, you can also implement measures such as vertical pod autoscalers or horizontal pod autoscalers that when CPU intensive workloads are being scheduled, you can have an autoscaler that will make sure that there are enough resources available both in memory and in CPU during the spiky hours. Going back to the point I introduced earlier in the talk, this kind of automations, the fact that Kubernetes allows us to do such automations basically allows us to handle such spiky behaviors and not just linear increases in utilization. It allows us to build a much more fault-tolerant workloads and procedures in our company. So spikes are not something to be worried of, and Kubernetes can handle those in an automated way.
So I think both examples that we've shown illustrate just the need for being able to see Kubernetes data that you wouldn't have been able to see if you were looking at these issues from a purely application way. So Noam's example, by the way, illustrates this more prominently because the issue had nothing to do with the application that, we'll say, Noam was developing. And it would probably require him to go ahead and talk with who knows how many other people before he was able to start investigating it. And I think that being Kubernetes native means that first off, you actually collect all of this data and put it in one place. And the second part is being able to show it in a way that is effective and a way that doesn't just give you a lot of signals that you have nothing to do with them, but actually take the only ones that matter and the only ones that matter to you and being able to show them in one place when you need it.
I completely agree, and I think that we need being Kubernetes native means understanding that applications, although they are running in isolated containers, are not isolated from each other effects. And also by being declarative and by automating a lot of stuff, basically our applications are utilizing Kubernetes APIs heavily, whether it's for service discovery or to, let's say, by the simple fact that Kubernetes can move around our workloads from one node to another, or to change or to prevent them from being scheduled on specific nodes. And other than Kubernetes, as our applications are getting smaller in size but larger in amount, interaction between services become something that is much more present in our applications. Applications are relying on interacting with each other. And when interactions between applications are so crucial to the entire business unit working, we need to make sure that when we troubleshoot a problem, we know exactly what happened in its blast radius application-wise, infrastructure-wise. I see that we have a question, Jill, from Johan.
Yes.
I hope I'm pronouncing it right. Johan, so basically to answer your question,
let me just read out the question so that everybody can know what we're referring to. So the question by Johan was, how would you easily sift through a large collection of logs for a given pod, especially when a pod has multiple containers, all of which are logging? Thank you, Johan, for the question.
Yeah, so following up on the context issue in Kubernetes, this is one of the most prominent issues that we had to think about here in groundcover. And we took several methods. We have several measures to deal with that kind of problem here in groundcover. So first of all, in our log screen, I can share my screen and even show it. You can get automatically, without needing to tag your log specifically, container level logs. So let's say I will take the last, if I will go to my production namespace, and then I'll open the pod tab, so I can open the container tab. If I have, let's say, a sidecar here, I can query only the specific containers in the logs tab. So if you have pods that have like a lot of sidecars inside, which is also a known practice in Kubernetes, Istio, for example, or Linkerd, you can isolate the logs at the container level. But the more troubling thing about logs and that we had to solve here in groundcover is basically how to get you as fast as possible to the relevant logs, as fast as, to only the relevant logs for a specific error. So what we did in groundcover, so I'll go now to our demo environment, our other demo environment, which is more apparent there. So basically, when you have an error, let's say I went to the traces and I saw a trace a 500 error in my front-end workload. If I will press on the workload in groundcover, I can see I have a logs tab. So I took a trace that wasn't having any logs at the side. Let me just quickly sift through it to see logs that was correlated to logs. So basically in groundcover, so I just took a trace that doesn't demonstrate it very well, but basically in groundcover, when you press on a trace, the logs tab will show you only the logs that happened +5 seconds, -5 seconds through the trace. So instead of having the classic experience of going through a trace, see it happened in 11:39, and then go to another system or to another tab and search for the time picker and search for the specific workload, and then start to iterate over a lot of logs that might not be related, you can easily in the traces tab see the logs that are relating to that specific trace. We do the same thing on the other way around. So I can go to log. Let's see if I will find a log now that is also related to some traces. So if I will press on a log on ground cover, I can see a more scoped glimpse of it. So I can see all the logs that happen plus 5 seconds, minus 5 seconds, and where this specific log is positioned inside. And also I can go to the traces tab and see what erring traces I had plus 5 seconds, minus 5 seconds from the moment of the log. So those two measures should allow you to quickly sift through only the relevant logs when you are investigating an issue. I hope it was clear.
Perfect. Thank you very much, Noam, and again, thank you, Juan, for the question. I hope this was insightful for you. I thought, for me, this was very insightful, and I hope for you users of the platform and non-users also, it got you a good glimpse into what you could do with groundcover and just in general the difficulties of monitoring Kubernetes as well as the advantages. So we're looking forward to hearing your feedback on this masterclass. As you probably know, we have those masterclasses once every 2 weeks. So there's another one coming up in 2 weeks. We're going to let you know about the content and what's going to be in it. For anybody who is not yet using groundcover, just go check out groundcover.com. You can start for free. There's a free tier you can use for up to 3 users. So go ahead and check it out. If you have more questions coming up as you digest everything that was shown today, feel free to reach out to us in the Slack community. And yeah, again, I want to thank everybody who joined today. We look forward to seeing you again in the next one. And of course, Noam, Aviv, thank you both very much for taking the time today. So let's sign off on that. Everybody, thank you very much. We'll see you on the next one.
Thank you, everyone. And thank you, Gilles, for hosting us for this session.
All right, my pleasure.
See you, everyone in the community.
Bye-bye.